back to the ChartSpark course series on fundamentals of integrated sensing and communications. Today, we are extremely pleased to present lecture 3.2 with the title of MIMO Precoding Design for ISAC. We are honored to have with us a very distinguished guest speaker, Professor Fan Liu from Southeast University, who will be leading today's session. Professor Liu is a renowned expert in this field, and we are more than excited to gain insights from his expertise. So please let me first introduce briefly Fan Liu. Professor Fan Liu is currently a professor with the National Mobile Communication Research Laboratory, Southeast University in Nanjing, China. His research interest lies in the general area of signal processing and wireless communications, and in particular in the area of integrated sensing and communications. He is the founding academic chair of the IEEE ComSoc ISAC ATI, the vice chair and founding member of the ISAC of the IEEE SPS ISAC Technical Working Group, and an associate editor of several IEEE transactions and journals. He was a recipient of numerous Best Paper Awards, including the 2025 IEEE ComSoc and ITSoc Joint Paper Award, 2024 IEEE Signal Processing Society Best Paper Award, and the 2023 IEEE Communication Society's Stephen O. Rice Prize. Okay, that's so much for my introduction today. Now, Professor Liu, it's your stage.
Okay, thanks, Yifeng, for your very nice introduction. So let me first share my screen. So can you see my screen now?
Yes, sure.
Okay, sounds great. Okay, so hello everyone. Welcome to I think this is the 5th lecture of this course series. And today we're going to introduce some recent progress, and also we'll review some previous results on MIMO precoding design for ISAC. So this series of works has been collaborated with many of my brilliant colleagues, including Professor Xiong here, and Professor Yafeng Liu, Professor Jie Xu, Professor Shi Jing, Professor Christos Masouros, Professor Athena Petropoulou, and Professor Yunina Elda. Okay, so I guess all of our audiences are very familiar with this slide. Actually, every lecture I will start with this one. So this is just a little bit of background of the ISAC. So if you don't familiar with this, I suggest that you can review the previous lectures. And today we're going to discuss also our MIMO precoding design to some extent can be characterized into this so-called joint design methodology. So remember that ISAC signaling design has mainly been divided into 3 categories. One is sensing-centric design, which is to embed information in the legacy radar waveforms. And the other is communication-centric design, which is to sense with standardized communication waveforms. And the third category is a joint design, which is to conceive novel waveform, or in particular in our lecture today is the precoding design based on nonlinear optimization techniques. Okay. So I'm not going to introduce more of the details here because I think in last lecture we have already introduced a lot about communication-centric design, and today we're going to focus on the joint design aspect. Okay, so let's directly start from the system model. So here, this is a generic MIMO ISAC precoding system model. Well, we have an ISAC base station that wishes to transmit a signal to both deliver information. For example, here, this signal may contain, some information bits, right? So this bits can be encoded by some, channel coding strategies. And here, in particular, we look at, Gaussian signaling. and to use this to deliver both, information and in the meantime to receive echo signals from the targets, and such that to extract the parameters of interest of the targets, like the delay, Doppler, and angle. So basically, we could have this kind of generic model. We have ISAC signal matrix here, and because we consider MIMO precoding, then this X is defined over the space-time domain. That so the number of rows of X represent the number of antennas, which is NT here, and the number of columns represent the time slots. So here is L, and here HC and HS, they are communication and sensing channels. ZC and ZS, they are AWGN matrices. Okay, so here this HC has a size of K multiplied K times NT. So K is a number of received antennas, or number of single antenna users, if you can see the multi-user MIMO. And here HS has a size of NS times NT. So NS is a number of sensing receiving antenna. Okay, NT is the transmitting antenna at the ISAC base station. Okay, so this is a very, very generic model, and all of the designs can be based on such a model. So it can be a single user MIMO, or it can be multi-user MIMO, or it can be so for the sensing model, it can be monostatic sensing, where you have a sensing receiver co-located with the ISAC base station, or it can be bistatic sensing but with a wild link connected both ISAC base station to the sensing receiver. So this is very generic. And under such a model, we would like to also provide more details about these parameters like channels and signals. So here in particular, we consider, let's see, multi-target angle estimation in this case. So MIMO radar channel. So for example, we have Q targets here, and we may have, each target has a direction of arrival, which is theta Q, and a direction of departure, which is phi Q. So, and also with reflection amplitude, which is beta Q. So this is a complex number. And for A and B, these are transmit and steering vectors. So one is with size NT, so transmit antenna array, and we consider in particular linear array, so uniform linear array with half wavelength spacing. And here this is B theta, which is a receiving steering vector, which is here. Okay, so these are all standard models. And for X, since we consider precoding design, then there are two types of precoding. One is linear precoding. Here, S is a symbol matrix. Okay, so it contains the data streams, like so it typically contains like quorum and PSK cancellation symbols. And this W is a precoding matrix. So X equals to WS. This is a linear precoding model. And we may also have nonlinear precoding, which means that this X cannot be modeled as a linear function of S. Okay, so it can be a nonlinear mapping from S to X. And both of these kind of designs have been explored in previous literature. And in the conventional ISAC precoding, there is a very classical approximation here. Here, as we can see, we usually assume that S is Gaussian, so such that the channel capacity of the MIMO Gaussian channel can be achieved by using this Gaussian signaling. And because S is Gaussian, then you can see X is also Gaussian if you're using linear precoding here, right? And if this is nonlinear precoding, then X is not Gaussian, right? But if you assume that you're using linear precoding, then we see that each of the column of xn, also subject to Gaussian distribution with a zero mean and a statistical covariance matrix Rx. Okay. So this, sorry, this should be the italic form. Okay, so it's like this. So here, if S is Gaussian, then the statistical covariance matrix of Xn should be WW Hermitian, right? So this is well-known results. But here, in many literature, we use sample covariance matrix to as an approximation of statistical covariance matrix with sufficiently large n. So if n is sufficiently large, this is x Hermitian over n is the sample covariance matrix of x. Then you can see this approximation may hold such that Rx equals to, so this red Rx equals to blue Rx, okay? But indeed, they're not different. Sorry, they are not the same. They're different. But here, in many classical approximations, we use this large n approximation such that these two matrices are equal to each other. Okay, so why we highlight these differences here? Because we'll soon see there's a difference between these two matrices in terms of the radar and communication matrix. Okay, so let's look a bit of the MIMO radar constraints or MIMO radar performance matrix. So first of all, we would like to highlight that many radar metrics are functions of the sample covariance matrix. Okay, so many radar function metrics are the functions of x Hermitian over n. Okay, so in such a case, you can see MIMO radar beam pattern, which can be written like this. So d theta. So this is actually the radiation power of the MIMO radar at a given angle theta. So it can be characterized by this guy. You have a Hermitian theta, which is the transmit antenna steering vector, and multiply to Rx and multiply to a theta. Okay, so this is a quadratic form, which is a function of the sample covariance matrix. And also there's another, commonly used constraint, which is waveform similarity. So in such a case, we have this X, which is our ISAC waveform or precoded signal should be, should be as close as possible to some benchmark radar waveform, like chirp signals. So we use X0 as a benchmark radar waveform here, and in the sense of the LP norm. Okay, so the LP norm of X minus X0 should be less than or equal to some given threshold. So this is a waveform similarity, and we believe that so if we have sufficiently small epsilon, then X, so the ISAC waveform should behave like a radar waveform. So we have a benchmark radar waveform here. Okay. And also there are CRB, so Cramér-Rao bound, which is known as the lower bound for all the unbiased estimators. And if you consider different parameter estimation problem, like for example, if we estimate the HS, the sensing channel matrices itself, then we could see that the CRB of HS is proportional to the trace of the inverse of the sample covariance matrix. Okay, so again, this Rx is the sample covariance matrix. And if you consider angle estimation, then the CRB of direction of arrival, so CRB of the DOA, may be written like this. Okay, it's proportional to this guy. It's a bit, little bit complicated, but this is actually the Schur complement formulation of the facial information matrix. Okay, so again, it is the sample covariance, is function of the sample covariance matrix here. And finally, we have, for example, linear minimum squared error. So this is different from CRB. Here, we may have some prior information about this HS. So in particular, it's, let's see, the second order moment of HS. So HS, Hermitian HS, and we take the expectation here, and we have RH, and we assume that this RH is known. So this can be done by, a long-term or short-term, data observation to compute approximation of RH. Then with this RH, we can perform linear minimum squared error estimation, so LMMSE. Then the LMMSE error can be written like this, okay? So again, it is the function of sample covariance matrix. So you can see RH is here, and this Rx is here, and we take the inverse, and then we take a trace outside of this inverse. So this is LMMSE. So as we said, many radar metrics are functions of this red Rx, so this sample covariance matrix, okay? But on the contrary, so very differently, we can see that communication metrics are functions of statistical covariance metrics, okay? So for example, Gaussian capacity, point to point, okay? So you can see that this Gaussian capacity, RC, is equal to this guy, while WW Hermitian is this blue Rx, right? Like we just defined here. So it is a statistical covariance matrix. And the sample covariance matrix here is WSS Hermitian, W Hermitian, right? So they're different. And multi-user interference. So this is also a very commonly used metric that we have been using in many previous works. For example, if you wish that the received signal at the receiver's HCX is as close as to the data symbol matrix S, then you can employ this multi-user interference MUI as the performance metric. So in particular, if you minimize this MUI without any constraints, so minimizing the unconstrained MUI will give you zero forcing precoder, right? Because in such a case, we know that the optimal solution of this X is the pseudo inverse of HS multiplied to S, right? So that is exactly zero forcing. So this is multi-user interference. And then we may have per user SNR under the linear precoding design, that each of this column of W, so WK, is the precoding vector of the kth user. So this is a useful power received at the kth user, and these are the so this is interference power from the other users other than K, right? So we have K, capital K number of users, and this is interference. This is a useful power. This is a noise power. So this is ISAK, the kth the SNR of the kth user. And if you can see the sum rate, that means you can add all the reads, achieved at each user together. You may have this R sum, which is the summation of from K to from 1 to K, log 1 plus SNRK. So this is Shannon formula. Okay. So as we can see here, many communication metrics are functions of this blue X, which is the statistical covariance matrix, or the square root of this blue X, right? So W is the square root because we have just defined this blue X is equal to WW Hermitian, right? So in any case, these communication metrics are functions of this statistical covariance matrix. So they are different, right? So the radar metrics, they are functions of sample covariance metrics, but the communication metrics, they are functions of statistical covariance metrics. Okay. Then you have two choices. So whether we're going to use statistical covariance metrics as a design variable, or to use these sample covariance metrics as a design variable, right? So if you can see the linear ISAC precoding problem, which means that we only optimize this W, right? Then in such a case, we know that the communication constraints can be a function of W. So we just use FC of W as the communication metric here. So one of these guys. So this should be larger than or equal to some threshold. And also we need the average power of the transmitted signal to be less than or equal to PT, right? And also we need, so this blue X is WW emission in such a case. But if you look at the, radar sensing metric, it is a function of the sample covariance matrix, right? So as we just mentioned, it's a function of this red X. But here we have to use this blue X because all the constraints, they are functions of the blue X. So in such a case, we have to use this approximation here, right? We have to use this assumption that N or L is sufficiently large such that these two matrices are, approximately equal to each other. How about we consider another, covariance matrix? How about we just use, the sample covariance matrix as a design variable, or just X as a design variable in such a case, because X is a square root of this red X. Okay, so that corresponds to nonlinear ISAC precoding or symbol level precoding. So why we say it is symbol level? Because we design X itself rather than design this, linear precoding. And this problem can also be a nonlinear mapping from S to X. Okay. So in such a case, we still have here the energy constraints rather than the power constraints. And this sample covariance matrix is, X exclamation over L. And here, because, we use this X as a design variable or sample covariance matrix as a design variable, then we will have to use that approximation again, such that we substitute this X or red X into communication constraints, right? And then it should be larger than or equal to some threshold. So again, we have to rely on this assumption, right? We have to rely on this. But so these kind of assumptions and this kind of precoding design problems have been, extensively investigated in many of our previous works, like these two papers. Okay, so one paper was published in 2018, and this paper was published in 2022. And these two papers, this one is about nonlinear or symbol level precoding. We use this kind of formulation. Okay, and this one, we can see the linear precoding, and we use this kind of formulation. But in both works, we have to rely on that assumption. And after all these years, we try to rethink, are these assumptions always valid? So we can see that they are, approximately holds under large L assumption, right? But what about we have, not long enough time slots? What about we have very short, frame structures? Then what about in such a case? Are the above assumptions still, valid? So can we still rely on these results? So that is the, the whole idea of designing new precoding, techniques for MIMO ISAC systems. So I will need to review this deterministic random trade-off again, which was, already been introduced in the, I think it's the third lecture by Professor Xiong in this TIT paper, that we found that sensing with random data payload signals may lead to performance degradation, okay? Because radar systems, they typically employ well-designed deterministic signals, but the communication data signals have to be random. So that is the main contradiction between communication and sensing. As you can see, this can be also reflected in this two problem formulation, that communication constraints, it is a function of the statistical covariance matrix, So that means the signal is already, random, right? But the radar function, the radar performance function is a function of sample covariance matrix. Is because in radar system, they just transmit deterministic signals. And for deterministic signals, sample covariance and statistical covariance, they're just exactly the same. So there's no such difference. But in ISAC system, we have random signals to doing both tasks. So in such a case, we have to differentiate between these two matrices. So then this leads to this deterministic random trade-off. So as you can see in these previous works that I have mentioned here, we haven't considered this trade-off, okay? So then we try to understand, so this is just an information theoretical work, but we try to understand in the practical, let's see, MIMO ISAC system, how can we design a precoder by, relying on this trade-off, the insights given by this trade-off, okay? So we look at the example here. We consider the LMMSC estimation, so which we have already mentioned here. Okay, and the aim of this estimator is to estimate HS itself. Okay, estimate the sensing channel itself. So after this estimation, we could, we could proceed with the follow-up estimation of the delay and the Doppler and angle parameters that was contained in this HS. So anyway, this LMMSC estimator is like this, which we have this X, which is the ISAC signal, and RH, okay, which is the correlation matrix of the sensing channel or second order moment, which is assumed known as some prior information about HS. And we also assume that HS follows a wide sense stationary random process. That means its second order statistical characteristics keeps unchanged. So under such estimating technique, the estimation error is like this. So we have just mentioned there. And if we use deterministic signal, SD, so D means deterministic, like in conventional MIMO radar or conventional channel estimation, MIMO channel estimation, we use orthogonal waveforms. We use, let's see, the orthogonal pilots. In such a case, SD Hermitian is an identity matrix. So then this assumptions strictly holds in such a case if you're using orthogonal pilots here. Okay, then you can see that the estimation error is like this. It is a function of W, the precoder. And if we're going to minimize this LMMSC estimation error, we will end up with this structure of the optimal precoder, which is known as auto-failing precoder. While this Q matrix is the singular contains the singular vectors of RH. Okay, and this lambda matrix will be, so it is a diagonal matrix whose diagonal entries will be determined by the auto-failing method. And this auto-failing structure is rather different from the communication rate maximization problem, but it is still a sort of auto-failing, okay? So LMMSC optimal precoding will give you a auto-failing structure of the optimal precoder like this. Now, let's think about if we sensing with random signals, if we do MIMO precoding, MIMO sensing with Gaussian signals, for example, we have to rethink this assumption in our previous works. So as you can see, in our previous works, we assume that the two matrices, so the blue X and the red X, they equal to each other. In such a case, we just assume that SS Hermitian over L is approximately identity matrix like this. Okay, if L is sufficiently large, and here SL, each of the column of S subject to zero mean and the unit variance complex Gaussian distribution. Okay. And we need that L is much larger than NT in such a case. For example, here this is the the approximation error measured by the the Frobenius norm. So under the case that NT ranges from 16 to 128, and you can see that even if you have not long enough frame length, then you still have very high approximation error. For example, if you need to keep the approximation error below minus 20 dB for NT equals to 32, which is here, this pink line, okay, then accumulation of approximately 4096 samples is required, which is here. Okay, if we need this approximation error to be minus 20 dB. So you can see that if we do not have such long enough frame length, then the randomness of the transmitted signals, which is Gaussian here, must be taken into account into our precoding design. Okay, so then we employ a new metric here, which is average sensing performance metric. So remember that we have this FS, which is the sensing performance metric, and which is a function of W and S. Okay, and here the randomness less in S, because S contains the random symbol matrix. So in order to characterize the average performance of the random signal sensing, then we need to take an expectation out of this F over S. Okay, so this can be treated as an ergodic sensing metric, which can be treated as a time average over random realizations of S. So we cannot just study one single realization of this FWS, because this is random. We have to look at its average performance. So we take an average outside this F and with respect to S. Okay. For example, if we consider LMMSE again, we will need to consider this ergodic LMMSE, which is so here we need to use that W and S both inside this trace of the inverse, and outside this trace we take expectation over S. So this is called ergodic LMMSE, which represents the average sensing performance achieved by this WS. Okay. Then under such objective function, which is apparently a stochastic optimization problem, then we may design two precoding techniques. One is the so-called data-dependent precoding, DDP. So in such a case, this W changes adaptively based on the instantaneous value of S. Okay, so given a realization of S, we will have to design a W. So that means data dependent, or in other words, symbol level precoding. Okay, and another sort of design is data independent precoding. That means W remains unchanged, such that W is independent of the signal realization. So for all the realization of S, we use a sim W. Okay, so that is data independent precoding. So apparently, this kind of design is has much lower complexity compared to this one, right? Because this W have to be designed for every S, but this W just designed once for all. But apparently, this DDP method may give you a better performance for both sensing and communication. We will show you these results later. Okay, and our here our communication metric is a point-to-point MIMO communication rate, which reads like this. As we just mentioned, it is a function of W, or it is a function of the statistical covariance matrix. And we consider point-to-point MIMO channel, and you may use this framework to could be extended to multi-user MIMO in our future work. So here we have IK. K is antenna number of the communication user. So we consider multi-user receiver, noise power sigma c square, and we assume that HC is perfectly known through channel estimation. So this is a very standardized standard assumption in MIMO precoding. Then our problem formulation can be formulated like this. We need that this sensing objective function, which is the ergodic LMMSE, to be minimized, subject to some communication rate constraints. Okay, so here this R0 is the required threshold of a communication rate. Okay, so this is a constrained stochastic optimization problem. So let's first look at sensing only precoding with the Gaussian signals. We have the first proposition is that the Gaussian signal, they lead to performance degradation of the estimation MSE, in particular here the ELMMSE. Why is that? Because we have Gaussian inequality. So JEMMSE, which is like this, which is defined here. Okay. So it is larger than or equal to if you put the expectation here. So why is that? Because Gaussian inequality tells us that EFX larger than or equal to FEX if FX is convex. Okay, so you can see this function is a convex function in WSS Hermitian W Hermitian, right? So you can use this inequality to prove that we have a lower bound here. Okay, and the lower bound is achieved when S is an orthogonal matrix or a unitary matrix, a semi-unitary matrix. Okay, so that gives you this guy, which is a deterministic LMMSE. So this is when you transmit orthogonal waveforms. Okay, so let's see what is the gap between in terms of this inequality. So this is the Gaussian lower bound, which is this black line, right? And we consider here NT equals to 32 again. And then if we improve this L from 32 to 2048, you can see this ELMMSE will become lower and lower. And finally, it approaches the Gaussian's lower bound. But it will need, let's see, more than, for example, here, more than 1,400 samples to make this, approximation error to be negligible, okay? Even if you have very small number of antenna, 32 antenna. And if you just use L equals to 32 times loads, you can see that the error gap, so the gap between this ELMMSE and the Gaussian's lower bound will be up to, let's see, nearly 5 dB here. Okay, so if we continue to minimize this deterministic LMMSE, where I actually minimize the lower bound of the ELMMSE instead of the exact estimation error. So this lower bound sometimes can be very, very loose, for example, like this. So only when you have very, very long frame, this lower bound can be tight, okay? So this observation motivates us to present efficient ELMMSE oriented precoding designs. Okay, so let's first look at the data-dependent precoding. So this is the sensing-only precoding, okay? So without communication rate constraints. So this is the original stochastic optimization problem here. And if we take the numerical approximation of this expectation by leveraging, let's see, n Gaussian signal samples, then we may end up with this guy, right? This is so this is the law of large number that if n is sufficiently large, then the sample average will equal to the expectation, right? So here, each of these FWSN is like this, and Sn denotes the nth Gaussian data realization. So for each data realization, we may have an estimation error, FWSN. So on the very large n, then we can approximate this expectation like this, that we have, n, samples, and we calculate the estimation error, and we take the sample average. So here we see that W will become a function of Sn. So it will become a function of the data. So then that gives us the data-dependent precoding. So in that case, we define Wn as W of Sn, okay? So then we can see the problem to minimize this Fwn Sn. So that means given Sn, given the nth realization of the data, we should design a W. So this is data-dependent precoding. And unfortunately, this problem under LMMC objective function has a closed form solution, okay? So it reads like this. So we have, so let Sn, so we first take the SVD of Sn, which is like this. So U, V, sigma, there are three matrices, okay? And then the optimal solution of the precoding matrix Wn looks like this. Again, we have this Q matrix here, which is the eigenvalue matrix, eigenvector matrix of the RH. And this theta n matrix, which is like this, defined like this. And this Bn matrix is defined like this. So this sigma is the, contains the eigenvalues of RH. And this P is a permutation matrix, okay? And this U matrix is the contains left eigenvector, singular vectors of Sn. So, and this, the sigma Sn, the lambda here, okay, lambda here needs to be designed through water filling, okay, through water filling. So you can see this is an auto-filling structure again, but with a more complex structure here. We have to also, so instead of just aligning to the channel using this Q matrix, we will also need to align with the data matrix, right? We use this U matrix. And in between these two matrices, we need some arrangement of the singular values of W and using auto-filling. Okay, so this is a structure that tells us what is the optimal solution looks like. Then with this closed form solution, we could define a set of the DDP matrices, so data-dependent precoding matrices, tailored for each Sn, expressed like this. And the ERMMC under the DDP scheme can be calculated like this, right? So you can see because this data-dependent design each W given a realization of S, so it generally attains the minimum ERMMC, but at the cost of substantial computational complexity, because we have to do this symbol by symbol. So each S will give you a W, and we have to do this iteratively. So this is a closed form solution for data-dependent precoding on the sensing-only scenario. And we could also consider data-independent precoding with Gaussian channels. So in such a case, we could use the stochastic gradient projection method to solve this stochastic optimization problem. In such a case, we use this, for example, the stochastic gradient. So we calculated the gradient given realization or given a realization of S, or we could use mini batch stochastic gradient, right? We just use a small batch of Gaussian samples to calculate this, gradient. And then this eta is the, the step size, also known as the learning rate. And we, after the, the gradient descent step, we projected this W over the, over this, the sphere constraints, because we consider, normalize the power right? So we normalize this W using this projection. So we could solve this problem by iteratively executing this stochastic gradient projection, steps. And this is very standard technique in deep learning, and we could also use this to solve our precoding method. So you can see that because we could design a precoder W once for all the data realization, so it generally strike a favorable trade-off between the performance and the complexity. Why is that? Because it is with very low complexity, we just design once for all, but the performance may be, worse if you compare this with the data-dependent precoding. Because for data-dependent precoding, we minimize each of this f given an Sn, but here we minimize the expectations on the average sense. So this is, will give you a little bit performance degradation. So this is data-independent precoding. Okay, so we could also explore the optimal precoding structure for the data-independent precoding, but we can only do this at the high SNR region. So if the SNR is sufficiently high, we could use this, asymptotic formulation of this expectation here. So here, this omega equals to WW Hermitian, and this pi matrix equals to Q omega Q Hermitian, while Q contains the eigenvectors of RH. And this kappa 1, kappa 2, kappa 3, they're with different values. Okay, so we actually use the Taylor expansion for the V-short matrix, because under such, so if you have S with as Gaussian matrix, then WSS Hermitian, W Hermitian would become a V-short distributed matrix, and we use that, and also according to the Taylor expansion of the trace of the inverse, we can end up with this asymptotic formulation. So we could see that this formulation can be very accurate if we have very high transmittance SNR, okay, like this. So they are very close to the numerical results. This asymptotic formulation. Okay, so you can see that so under the high SNR, we could also get rid of this expectation, because in typical scenarios, we're unable to derive the closed form of this expectation, because the inside this expectation, we have this trace of the inverse, which could be very nonlinear and very complicated. We cannot have a exact closed form for that. So we use this high SNR approximation, and under this approximation, we could minimize this guy, right? Rather than minimize the stochastic objective function. So this problem, minimize this guy, is a non-convex problem, but we could actually prove this theorem that the optimal solution of the problem has also a structure that the omega, this omega, which is WW Hermitian, shall be aligned to the subspace of RH. So we use this Q matrix again as the eigenvalue eigenvector matrix, and this C contains the eigenvalue matrix, which needs to be optimized. And with this theorem, we could simplify this problem into this one. Okay, so such that we have significantly reduced the solving complexity, because here we need to solve for n by n matrix, right? But here we just need to solve for a size n vector, right? So the complexity has been reduced significantly, and this is a non-convex problem, but we could use successive convex approximation to solve this problem. Okay. So these are some convergence examples for the SGP for single for the data independent design, and SCA for the high SNR region. So they are both convergent to our optimal results under moderate number of iterations. And if we compare the performance under the two design techniques, the data independent, data dependent, and also water failing, so the deterministic precoding, then we could see that data dependent precoding indeed provides the optimal performance, right? Because it is designed for each realization of S, and the data independent is a little bit, has a little bit performance degradation compared to DDP, but it has, much more, lower sensing error compared to the conventional water failing design. So by conventional water failing, I mean to, ignore the randomness, and we just use this structure, this deterministic, precoding design to, precode our data signals, which will end up with this kind of, estimation error. So which is higher than the designs that take the randomness of Gaussian signals into account, right? So this is the performance comparison on the sensing only scenarios. And under the high SNR region, we could see that, so again, we could also have very good results in terms of the DDP. And under the high SNR region, we could also solve for this problem, and we get also very good results. And they are both better than the water failing. Here, this is the resultant estimation error for deterministic and random signals. So this LMMSE is the lower bound, right? The lower bound, and you can see when with our SDP method, which is a data independent precoding, we could approach the estimation error of the deterministic signal when L equals to 256. Okay, so it's like this. So when L grows large, then we could approach the deterministic performance. Okay, so this is the sensing only scenario results. Then let's look at ISAC precoding with Gaussian signals. So ISAC precoding instead of sensing only. So in such a case, we need to impose communication rate constraints. Okay. So we look at this problem, and we could also, solve this kind of problem by using DDP or DIP. And but due to this, the involvement of this rate constraints, we have to develop penalty-based, method to solve this problem. So we first look at the DDP again, but in such a case, if we can consider data-dependent precoding for ISAC, then this Wn, so this W will also become a function of S. Then this makes Ws non-Gaussian. Okay, so if Ws is non-Gaussian, we are unable to use this log determinate equation again, but we could prove that under such a case, if W is a function of S, then the ergodic rate or the mutual information in such a case conditioned on HC is strictly smaller than C. Okay, so C is the capacity of communication channel, and the formula in the left, and this. So in such a case, this guy is achievable. Okay, so in such a case, if we could use this as a constraint, then we could see that the channel capacity is also constrained by this R0. Okay, so we could safely use this log determinant as the lower bound of the channel capacity, and in such a case, we are using a threshold to constrain the lower bound rather than the exact channel capacity. Okay. Then for DDP, we could use this. We minimize this FWNSN, and this RWN is like this, right? And we needed to, and here we introduce auxiliary variable, which is WWN Hermitian and equals to omega n. And in such a case, the rate can be written in this formula. And then we consider each sub-problem like this. We minimize this F, W, N, S, N, subject to R omega N, and we have this omega N equals to W N, W N Hermitian. So why we employ this kind of formulation? Because in the objective function, W N and W Hermitian, N Hermitian, they cannot, they are not, you know, they cannot approach each other. There is a very, you know, there is this SNS Hermitian in between the WN and the WN Hermitian in such a case. So we cannot get rid of it. So we just introduce this auxiliary variable here to solve for each of these subproblem. And then in such a case, we can panelize the equality constraints into the object function like this. And then we could solve this problem by iteratively solve for W and omega, okay? And for each iteration, we increase this rho such that we could have, you know, reach the convergence of the algorithm. And for DIP, we could do the same, but the only difference is that we have to change the objective function into this stochastic objective function rather than this you know, instant realization of the MMC. So again, we could solve this for the SDP and alternative optimization method by using a penalty method. And here are some convergence example. As you can see that after some number of iterations, we could reach the convergence, and the read constraints will not be violated in such a case. And we compare our performance, our the DIP and the DDP with the deterministic optimization problem, and we could see with here with the deterministic optimization problem compared to the DIP, we could have 4 BPS per hertz improvement under the case that N equals to, I think here is, let's say 32, and L equals to 24. And here for the case with 32 number of antennas, we could have 3 BPS per hertz performance gain. And for the DDP, we could improve, significantly more compared to the deterministic optimization problem. And also DIP, we could achieve 1.5 dB gain compared to the DIP case, okay? And here, this is the frame length symplectic performance of Gaussian signals. So as you can see, if under the case that R0 equals to, for example, 0.92 water filling rate, so this is the channel capacity of the Gaussian channel, and then the DIP and DDP result in the same MMSC under the case that L equals to 144, okay? So that means given a moderately large L, we could simply use DIP compared to using the more complicated DDP case. Okay, so I would like to wrap up for this talk. So here are some take-home message. So for the random ISAC signals, we need to develop some new sensing metric. For example, the ergodic linear minimum mean squared error. So this is just an example. You could think more of this kind of metrics, like we could have ergodic CRB. We could have, for example, ergodic or average detection probability, or average MMSE in such a case. Okay, so we have talked about dedicated precoding for random MIMO ISAC signals, so DDP and the DIP. Okay, so in the random ISAC signaling situation, we have to take this randomness into account. We cannot just use the conventional deterministic optimization techniques. And the advantages here is to more accurately characterize the performance of random ISAC signals, and we have some new degrees of freedom to control the ISAC trade-off on the random signaling. Okay, so finally, we reached to the conclusion that random ISAC signals deserve some dedicated precoding. So if you are interested in the details of this talk, you could look at this paper, so reference 6, so which was published last year in TSP with the title Random ISAC Signals Deserve Dedicated Precoding. And if you are interested in other topics on the random ISAC signaling, you could look at this paper, these 3 papers, and also these papers are all this paper is also about the random signaling, and this is the TIT paper that which has already been discussed in previous lecture, and we could see that these papers, they are just application of the theory in this paper. Okay, so if you are interested in these results, you could look at these references. Okay, so that's all from my talk. Thanks for listening.
Okay, thank you. Thank you very much, Professor Liu, for your very inspirational and insightful lecture. We now have, I think, 2 questions from our audience. Okay, the first question is it possible for a design to achieve an ideal beam pattern, for example, low side lobes, but still result in very poor Cramér-Rao bound for parameter estimation, or vice versa?
Okay, so this is a very tricky question, I would say, because actually, if you have an idea beam pattern, so first of all, we have to define what is an idea beam pattern. So in my opinion, idea or a perfect beam pattern shall be a delta function in the angular domain, right? So in such a case, you would not have any set lobe. You would have 0 set lobe in such a case. So that is the ideal beam pattern. But in such a case, the CRB will also be the optimal, I would say. So this is the case when you have a delta beam pattern. But in practical systems, scenarios, you will never get such a perfect beam pattern. You would have a mean lobe with some mean lobe width, and you would have some set lobe levels. But as you just suggested, if you just reduce the set lobe level, can we still get a poor Cramér-Rao bound? I think it is still possible. So even if you have very low set lobe, you may have very wide mean lobe in such a case, because CRB actually mainly depends on the mean lobe of the beam pattern or the ambiguity function. So if you have a very wide mean lobe, that means you have a very you have a very high uncertainty about the angle of a target. Okay, so in such a case, you would end up with very poor CRB, but you still have low set lobe level. That means if you consider multiple target detection, then this other targets may have very small interference to the target you are currently under examination. But still, you may have very poor CRB because you have very wide mean lobe. So I think you could design such a beam pattern, but such a beam pattern may only be useful in the case that you have very you do not so you have high uncertainty about the angular region of the targets. Yeah.
Thank you, Professor Liu. I recognize that you just mentioned that CRB really characterizes the characteristic of the ambiguity function around its main lobe. So is there any reference or results, analytical results related to your claim?
So I think you could read the book of Stephen Kay. I think under the but I don't think he explicitly mentioned ambiguity function in his book, but under the chapter of maximum likelihood estimation MLE, and also the chapter of CRB, you could see that CRB measures the the Fisher information measures the curvature of the likelihood function, right? And if you derive the equation of MLE under the single target scenario, you would see the results that the likelihood function is exactly the ambiguity function under the single target scenario. But for multiple target case, they are not equal. So I think you could just derive the equation by yourself about the MLE, and you will see the connection.
Thank you. Our next question is, how do you develop a precoding strategy for Gaussian signaling, which can how can you translate this Gaussian signaling precoding strategy to practical systems using discrete constellations such as QPSK or 16 QAM? Is there a significant performance loss after this translation?
So we could still develop precoding strategies under these discrete constellations, but we can, so under such circumstances, we cannot directly use the strategies, so for example, we cannot rely on this, we can still rely on this closed form solution, but we have to, first calculate the SVD of the QPSK or QAM symbol matrix rather than the Gaussian symbol matrix. And after that, we just simply substitute the results, this U matrix here, and also the sigma matrix here. Then we could have this precoding method. And I would see if you directly use the Gaussian SVD here, you will not have the good performance. But for QPSK and QAM, you just use the same design strategy and just do the SVD, you could get the result here. So the whole framework still applies to discrete constellation, including this SGP method. So you could just produce the QPSK or QAM samples of this S and to calculate the stochastic gradient. And also something like here you have this DDP method where you rely on this ICA or rely on this SGP. You could still use QPSK or QAM. So these methods, they don't rely on the properties of Gaussian. But there's one thing truly rely on Gaussian properties, which is I think here under this high ISNR region. So we use the property of Wishart matrix. Here we use the inverse moments of the Wishart matrices, and in such a case we have to rely on Gaussian. So this high ISNR design cannot be directly adapted to QAM and PSK, but other than that, all the techniques proposed in this talk can be applied without any changes.
Okay, thank you. So I guess this is all for today's session. So thank you again, Professor Liu, for your inspirational lecture. If you are interested in today's lecture, please continue to pay close attention to our Taskbar course series. Thank you all for listening.
Okay, thank you. Bye-bye.
感谢两位老师。